There is a possibility in modern physics that makes many scientists feel uncomfortable. And the strange thing is that it is not unscientific or rational in the slightest. You see, most people think science exists to make reality clearer, more stable, and easier to understand. But sometimes the opposite happens. There are ideas that physicists often do not like to present too directly to the public, not because they are crazy, but because they can make people realize that the foundation of reality may be less solid than we once believed. In science, the most frightening thing is not some bizarre hypothesis appearing in the press. The frightening thing is when mathematics begins to point in a direction that human intuition does not want to accept. And the deeper we research the origin of the universe, the more we realize that the Big Bang may not be the absolute beginning. Perhaps the most worrying thing is the possibility that something existed before us, and the universe still retains traces of it. Most people believe that as science advances, reality will become simpler, that eventually everything will be encapsulated in a few beautiful equations. But modern physics is doing the opposite. The deeper we look, the more we see the foundation of reality beginning to blur. Einstein's general relativity worked wonderfully when describing galaxies, black holes, and the motion of the universe on large scales. It is accurate to an almost frightening degree. But when you run those equations backward to the time near the Big Bang, everything begins to explode in the literal mathematical sense. Density approaches infinity. Space-time curvature approaches infinity. The equations stop working. Then on the other side you have quantum mechanics, the theory that describes the subatomic world with unprecedented accuracy in the history of science. Quantum mechanics explains transistors, lasers, atoms, and nearly all modern technology. But when you try to combine it with gravity at extremely high energies, the two most successful theories in physics begin to clash with each other like two languages that cannot fully reconcile. And when that happens, a physicist will immediately think of one very simple thing. Our understanding is not yet complete. We call that limit the Planck time, a period of time so small it is almost unimaginable, about 10 to the power of 43 seconds after the Big Bang. Before that point, our current equations lose almost all meaning. That is the part that modern physics cannot yet see through. What is important here is that Big Bang theory does not actually explain why the universe exists. It only describes how the universe evolved after that process had already begun. Many people confuse a descriptive model with a final explanation, but in science, those two things are completely different. And then a possibility begins to emerge, a possibility that makes many physicists feel more uncomfortable than they want to admit. Time may not have existed forever. Perhaps time itself was created along with the universe. If that is true, then the question, what happened before the Big Bang, may be more dangerous than we think, because the word before may have lost its meaning at the deepest level of reality. The universe may not have begun only once. Perhaps what we call the Big Bang was not the first moment of everything, but only a phase in a sequence of cycles stretching nearly endlessly. You see, many physicists are beginning to feel dissatisfied with the singularity, because in physics, an infinite point is often not the final answer, but a sign that the theory has gone beyond its limits. Therefore, some models are beginning to replace the singularity with a different idea. Instead of the universe appearing from absolute nothingness, it may have once contracted to an extremely dense state and then bounced back in a big bounce. This sounds like science fiction at first, but it actually comes from very serious efforts to save the equations from mathematical collapse. And if the universe once went through a contraction phase before expanding, then a very dangerous question begins to appear. Could some information from the previous universe still remain? Some physicists believe it is possible. Roger Penrose, for example, has proposed a model called conformal cyclic cosmology. His idea is extremely strange, but also very beautiful mathematically. In this model, the heat death of a universe, when all stars have gone out, matter gradually decays, and entropy reaches its maximum, can become the initial condition for a new Big Bang. It sounds unreasonable, but think about it carefully. When matter disappears completely and only radiation remains, the concept of size begins to become strange. Photons do not experience time the way we understand it. At that level, an extremely large and cold universe can become mathematically equivalent to an extremely small and hot universe. That is one of the ideas that makes many physicists both fascinated and uneasy, because it suggests that end and beginning may be just two different ways of looking at the same physical process. And this is not pure philosophical speculation. Models like these exist because modern cosmology has real unsolved problems. Inflation theory, for example, is an extremely successful idea. It explains why the universe is flat, uniform, and as large as it is today. But then inflation opens up a new question. What caused inflation in the first place? And if inflation happened once, many equations show it could happen forever in different places in space-time. This idea is called eternal inflation. In that picture, our universe may be just a small bubble universe, emerging among countless other bubble universes, each possibly carrying slightly different physical laws. That is when many physicists begin to feel truly uncomfortable, because our universe gradually no longer looks special. For many centuries, humans have been continuously pushed out of the central position. Earth is not the center of the solar system. The solar system is not the center of the galaxy. And now modern cosmology is beginning to suggest that even our entire universe may not be special. What makes the scientific community uncomfortable is not the ideas themselves, but the fact that many of these models work surprisingly well mathematically and do not clearly contradict observational data. That is the part that makes everything frightening. Science is most dangerous when an idea once considered philosophy begins to approach the region where it can be tested with real data. And right now, some researchers are actually looking for traces of previous universe cycles in the cosmic microwave background, the fossil light remaining from the early universe. We may be seeing random noise patterns, but it may not be. And if a previous universe once existed, if it truly left traces inside the structure of the current universe, then the most frightening thing is probably not the existence of something before the Big Bang. What is much, much more frightening is the possibility that the universe has existed for infinitely longer than anything the human brain can truly imagine. And then everything begins to become even stranger when we look at what is considered the strongest evidence for the Big Bang, cosmic microwave background, or CMB. You can think of it as the fossil light of the universe. It is the radiation remaining from about 380,000 years after the Big Bang, when the universe had cooled enough for light to travel freely through space for the first time. Before that point, the universe was like a hot plasma fog, where photons could not travel far without constantly colliding. But when the plasma cooled, the light was released and began its journey lasting billions of years until our modern telescopes detected it. What is astonishing is that the CMB is almost perfectly uniform. Its temperature fluctuates by only a few parts per million degrees. And it is precisely those tiny fluctuations that contain nearly all the information about the initial structure of the universe. Satellites like COBE, WMAP, and later, Planck have mapped the CMB with astonishing precision. But then something uncomfortable begins to appear. Some details in the data do not completely match what standard cosmology predicts. One of the most famous examples is the so-called cold spot, a region of the sky that is significantly colder than normal statistical predictions. Now, in science, you always have to be extremely careful with things like this. An anomaly does not automatically become a new physics revolution. Many anomalies eventually disappear when better data appears. But the problem is that the cold spot has not completely disappeared. Some researchers try to explain it with supervoids, that is, extremely empty regions of space that alter the energy of photons passing through. Others argue that it may just be a rare random fluctuation. But up to now, no one is completely satisfied with those explanations. And the cold spot is not the only thing that makes cosmologists uneasy. There are large structures in the universe that seem to be aligned in a very strange way. Some patterns in the CMB seem to have a preferred orientation instead of being completely random as the standard model expects. Researchers sometimes call it by a rather humorous name, the axis of evil, although most physicists hate that name because it sounds too sensational. But the phenomenon itself is real. Some large-scale fluctuations in the CMB appear to be linked in a way that is difficult to explain with standard cosmology. Now, the important thing is to keep a clear head here. These anomalies do not prove that there was a universe before the Big Bang. They do not prove the multiverse. They do not prove any extreme ideas. But in science, small details are sometimes where revolutions begin. Remember that the tiny anomalous orbit of Mercury was once a small problem before Einstein explained it with relativity. Blackbody radiation was once a puzzling detail before quantum mechanics emerged. In physics, nature often whispers before it shouts, and that is why scientists are very cautious. The scientific community always tries to find normal explanations first. That is how science should work. You do not jump straight to the strangest possible conclusion. You check for data errors. You check instrument noise. You check selection bias. You check foreground contamination. And most of the time, the anomaly disappears. But what makes many cosmologists feel uncomfortable is that some of these anomalies are still there, even as the data gets better and better. Not strong enough to break modern cosmology, but not weak enough to be completely ignored. They are like small cracks on a wall that seems perfect. And what is dangerous about small cracks is that sometimes they show that underneath there is something much deeper. Some researchers are beginning to wonder whether those patterns could be traces of physics before the Big Bang. They could be traces of collisions between bubble universes. They could be signals remaining from a previous universe cycle. Or they could be nothing at all. But that is exactly what makes modern cosmology so incredibly strange. We are looking at the oldest light that ever existed, trying to read the history of reality from fluctuations smaller than 1 part per million degrees. And sometimes I think what keeps physicists awake at night is not the answers. It is the possibility that these small deviations could be the first thing we see from a much deeper layer of reality beneath our familiar universe. To understand why those anomalies make cosmologists so worried, we must talk about entropy, because ultimately almost every path in modern cosmology leads to it. Now, most people hear the word entropy and immediately think of heat or chaos in some rather vague sense. But entropy is actually much deeper. It is directly related to the structure of time, to why the past is different from the present, and why the universe has a history in the first place. Simply put, entropy measures the number of states a physical system can exist in. And in nature, systems almost always move from states with fewer possibilities to states with more possibilities. Imagine you have a brand new deck of cards arranged in perfect order. If you shuffle it once, it may still look somewhat like the beginning. But if you keep shuffling it thousands of times, the deck will almost certainly become completely chaotic. What is important here is that there is no mysterious force pushing the deck toward chaos. It is simply because the number of ways for the deck to be chaotic is vastly greater than the number of ways for it to be in perfect order. And entropy works almost the same way across the entire universe. A glass falls to the floor and shatters into hundreds of pieces. You have never seen hundreds of glass pieces jump back up and reassemble into a complete glass, not because the laws of physics forbid it. The basic equations almost allow both directions of time. But the state of the intact glass is vastly more special than the state of the pieces lying in chaos. This leads to a very important idea. If entropy always increases, then the past must have had lower entropy than the present. And cosmology immediately encounters a huge problem, because when we look at the early universe, we see it had astonishingly low entropy. That is the real strange thing. Many people think the biggest mystery is why the universe today is chaotic and complex. But for many physicists, the real question is why the universe was so orderly right from the beginning. If the universe had begun close to maximum chaos, galaxies would not have formed, stars would not have formed, planets would not have formed. There would be no complex chemistry, no life, no person sitting here thinking about cosmology. All the structure we see today depends on the early universe having been in an extremely low entropy state. And that is where everything begins to become very uncomfortable, both philosophically and physically. Because modern physics can describe how entropy increases, but it cannot explain why the initial entropy was so low. Roger Penrose once tried to estimate the specialness of this initial state, and the number he got was so large it is almost impossible to imagine with human intuition. It is not just rare. It is rare to the point that the entire universe seems like an almost impossible exception in the space of possible physical states. And it is precisely that initial low entropy that creates what we call the arrow of time. That is why you remember the past and not the future. That is why you age instead of growing younger. That is why physical systems move toward chaos instead of perfectly reorganizing themselves. In a very real sense, our perception of time may be nothing more than a consequence of increasing entropy. And the more seriously we think about this, the less intuitive reality becomes. Because if the fundamental laws of physics are almost symmetric in time, then why did the entire universe begin in a state so special that it allows time to have a direction? That is one of the deepest questions in modern cosmology. Some physicists even argue that understanding entropy is more important than understanding the Big Bang itself, because the Big Bang only describes the early evolution of the universe, while entropy touches on why any history could exist in the first place. And then an extremely strange consequence begins to emerge from this very logic. If chaotic states overwhelmingly dominate ordered states, and if the universe exists long enough, then small random fluctuations will have a higher probability of appearing than enormous structures like our entire cosmos. It is entropy itself that has led physicists to one of the most frightening ideas ever to appear in modern cosmology. What keeps many physicists awake at night is this: when considered purely by statistical logic, our universe should not look like this. It is too orderly, too stable, too complex in an extremely improbable way. In statistical mechanics, we often think of all possible states of a physical system as points in something called phase space. You can imagine it as a gigantic space containing every way matter and energy can be arranged. And in that space, chaotic states overwhelmingly dominate ordered states. That is what entropy really tells us. A tidy room is extremely special. A messy room has countless ways to exist. A deck of cards arranged in perfect order is rare. A random deck has a nearly infinite number of configurations. The problem is that when you apply that logic to the entire cosmos, everything begins to become very strange. If entropy dominates all physical systems, then a stable universe lasting billions of years with galaxies, stars, planets, chemistry, and life is not the most natural state. It is an extremely special state, and the more complex structure is required, the lower the probability of spontaneous appearance drops to numbers that are almost impossible to write down. Think about that for a moment. A galaxy is more complex than a random cloud of gas. A solar system is more complex than a chaotic galaxy. Life is more complex than inorganic matter. A human brain with memory and consciousness is far more complex still. Each additional layer of structure requires a lower entropy state. That is, a more special state. That is, a lower probability. And this very logic leads many physicists back to an old idea from the 19th century by Ludwig Boltzmann. Boltzmann tried to explain why the universe appears orderly by suggesting that the entire observable cosmos is just a rare fluctuation in a larger state of thermal equilibrium. The idea at first sounds reasonable. If the universe exists long enough, random fluctuations will eventually create regions of low entropy. No need for miraculous initial conditions. No need for special design, just enough time. And this is the part that makes everything begin to shift from astronomy to existential physics. In thermodynamics, a rare fluctuation is not forbidden. It is just extremely unlikely. But if time stretches nearly to infinity, then even nearly impossible events will eventually happen. You can think of it like flipping a coin. Flip it long enough, and eventually you will get a long streak of all heads. Not because nature wants it to happen, but because the small probability eventually wins if you give it enough time. Boltzmann began to wonder whether the entire universe could be just such a gigantic fluctuation. And here the logic becomes extremely dangerous. Because if a fluctuation can create a universe like ours, then smaller fluctuations will always have a higher probability than larger fluctuations. A fluctuation that creates a galaxy is easier than a fluctuation that creates hundreds of billions of galaxies. A fluctuation that creates a planet is easier than a fluctuation that creates an entire stable cosmos lasting billions of years. Nature always prefers the cheaper path in terms of entropy. And that is when cosmology begins to become frightening in a very special way. Not the frightening kind from science fiction movies, but the frightening kind when mathematics continues to work while human intuition begins to collapse. The important thing is that this is not fantasy. It is not speculative nonsense. This is the direct consequence of thermodynamics, probability theory, and statistical mechanics when you apply them on the scale of the universe. Many physicists do not like to speak too strongly about this because it is easily turned into sensational philosophy. But the logic underneath it is completely serious. And when you push that logic one step further, you begin to realize something extremely uncomfortable. If the universe is just a fluctuation, then the smallest fluctuation sufficient to create an observer will always have a higher probability than creating the entire cosmos we see around us. To understand why that logic is so dangerous, we must go deeper into one of the strangest things that quantum mechanics has ever revealed. Space is not actually empty. Now, when most people think about vacuum, they imagine a completely void nothingness, a place with no matter, no energy, nothing at all. But in quantum physics, the vacuum has never truly been that quiet. Even what we call empty space is constantly vibrating at the microscopic level. This is where classical intuition begins to collapse completely. In quantum mechanics, there is a very famous principle called the uncertainty principle. Most people hear about it in the form that position and momentum cannot be determined with absolute precision at the same time. But there is another version directly related to energy and time. It says that the energy of a system can fluctuate over extremely short periods of time, as long as that fluctuation disappears quickly enough. This sounds almost absurd if you grew up with classical intuition, but nature does not care what sounds reasonable to us. And the consequence is that the vacuum begins to behave in a very strange way. Quantum fluctuation continuously appear and disappear inside what is called empty space. Pairs of particles and antiparticles can form in extremely short times and then annihilate each other before. You can observe them directly. They are often called virtual particles, and that name sometimes causes misunderstanding. They are not imaginary objects in the sense of being unreal. They are very real consequences of quantum field theory. In fact, many physical effects have been measured with astonishing precision thanks to those fluctuations. The Casimir effect, for example, shows that two metal plates placed very close to each other in vacuum will attract each other simply because of the quantum fluctuations of the vacuum. The Lamb shift in the hydrogen spectrum is also a direct consequence of vacuum fluctuations. This is no longer philosophy. This is physics that can be measured by experiment. And that is where everything begins to become extremely uncomfortable for cosmology. Because if the vacuum is not truly empty, if space itself already contains continuous quantum activity, then the idea of the spontaneous emergence of physical structure is no longer completely crazy. Now, be careful here. This does not mean the universe appeared from nothing in the way many sensational headlines like to say. The quantum vacuum is not philosophical nothingness. It is a physical state with extremely complex mathematical structure. But that is exactly what makes the problem even more frightening. The space that we once thought was the passive stage of reality turns out to be full of invisible activity. And quantum mechanics has taught us a very uncomfortable lesson throughout the 20th century. What humans consider irrational is often exactly how nature operates at the deepest level. An electron can behave like a wave, A particle can tunnel through a barrier that classical physics says is impossible to cross. A particle can exist in superposition until measurement occurs. The vacuum can fluctuate. Nature continuously destroys our classical intuition time after time. And the problem is that the equations keep being correct. That is the part that both fascinates and keeps physicists awake at night. If quantum mechanics were just a weird idea but did not work, we would have abandoned it long ago. But quantum mechanics is the most accurate theory ever built in the history of science. It predicts experimental results accurately to more than 10 decimal places. That means when intuition and mathematics conflict, the history of physics shows that intuition is usually the one that fails. And then cosmology begins to ask an extremely dangerous question. If the vacuum can fluctuate continuously at the microscopic level, then can larger fluctuations occur? Can space-time spontaneously create increasingly complex structures if it exists long enough? At first, this question sounds like science fiction. But when you combine quantum fluctuations with entropy and statistical mechanics, you begin to see a very frightening logic gradually taking shape. A small fluctuation is more likely than a large fluctuation. A simple structure is more likely to appear than a complex structure. And if the vacuum is truly never completely silent, if space continuously fluctuates throughout infinite time, then sooner or later cosmology will be forced to face the next question. The question that makes many physicists feel more uncomfortable than any other idea in modern physics. That is where statistical mechanics begins to lead us into a very dangerous region of cosmology. Because in physics, an extremely unlikely event does not mean it never happens. That is extremely important. Human intuition often confuses very difficult with impossible, but nature does not operate in such an emotional way. If a system exists long enough, even nearly unimaginable fluctuations will eventually appear. Imagine you have a room full of gas. According to entropy, the molecules will be distributed almost evenly throughout the room. But mathematically, there is no law of physics forbidding all the molecules from accidentally concentrating into a single corner. That probability is extremely small, almost impossible to occur within the current lifetime of the universe. But almost impossible is not the same as impossible. If you wait long enough, truly long enough, that fluctuation will eventually happen. That is the deepest nature of probability theory. And when time approaches a nearly infinite scale, things that seem absurd begin to become something that must be taken seriously. Ludwig Boltzmann understood this from the late 19th century. He tried to solve a question that troubled physics at the time. If entropy always increases, why does our universe appear so orderly? Boltzmann proposed a bold idea. Perhaps the entire observable cosmos is just an extremely rare fluctuation appearing inside a larger system that is in thermal equilibrium. At first, that idea really sounded quite reasonable. You do not need to assume the universe began in a mysteriously special state. You only need a system that exists long enough for rare fluctuations to eventually appear. According to that logic, the initial low entropy of the universe is no longer a miracle. It is just an extremely rare statistical accident. And at first, many physicists felt this could be a rather elegant escape from the entropy problem. But then everything began to go off track in a very uncomfortable way. Because once you accept fluctuation logic, mathematics begins to pull you toward a much stranger conclusion. Think about it very carefully. If a large enough fluctuation can create the entire observable universe, then smaller fluctuations will always be more likely than larger fluctuations. A fluctuation that creates a star is easier than one that creates a galaxy. A fluctuation that creates a planet is easier than one that creates billions of planets. A fluctuation that creates a living creature is easier than one that creates the entire evolutionary history of life on Earth. Nature always prefers the cheaper path in terms of entropy. That is where the logic begins to oppose human intuition in an almost cruel way. We like to think that we live in a vast universe with a history stretching billions of years, with hundreds of billions of galaxies evolving according to stable physical laws. But statistical mechanics does not care what seems reasonable to human emotions. It only cares about probability. And according to pure probability, a smaller fluctuation always dominates a larger one. That means if our universe is only the result of a random fluctuation, then a gigantic cosmos like this is actually too expensive in terms of entropy. It contains too much structure, too much history, too much information. Do you see the problem starting to appear yet? This is the part where cosmology shifts from astronomy to existential physics. At first, we were just trying to understand stars and galaxies. But now physics begins to question the very logic of the reality we are experiencing. And the most frightening part is that every step in this argument comes from very serious principles of physics, thermodynamics, statistical mechanics, probability theory. There is no mystical leap here. Only mathematics pushed to its final consequences. Throughout the history of physics, every time that happens, humans usually react the same way. First denial, then discomfort, then finally realizing that nature has no obligation to be comfortable with her intuition. Quantum mechanics once did that. Relativity did too. And now modern cosmology is beginning to do the same. Because if you continue to follow fluctuation logic all the way, you will realize something extremely frightening. A fluctuation that creates less structure will always have a higher probability than a fluctuation that creates an entire stable universe lasting billions of years like ours. If you truly follow fluctuation logic to the end, you will realize that a minimal observer is always more likely to appear than an entire complete universe. Think about that very slowly. To create the entire cosmos as we see it, hundreds of billions of galaxies, billions of years of stellar evolution, chemistry, biology, Earth's history, and all of human civilization, entropy must decrease in an extremely special way. That is a gigantic fluctuation. But if all you need is an observer capable of experiencing reality for a few seconds, then the necessary fluctuation is vastly smaller. According to statistical mechanics, nature always prefers the least expensive path in terms of entropy. And that is when physicists begin to realize an extremely uncomfortable conclusion. Instead of creating an entire stable universe, a fluctuation is far more likely to create only a single brain existing for an extremely short time between vacuum fluctuations and then disappearing right after. That brain is called a Boltzmann brain. It sounds more like science fiction than physics, I know. But what keeps physicists awake at night is this. That idea did not appear because someone wanted to write weird philosophy. It appeared because mathematics led there. A Boltzmann brain, according to this logic, could appear together with an entire set of false memories about a past that never existed. It could believe that it is sitting in a room, remembering childhood, remembering Earth, the stars, and human history, even though none of those things ever actually existed. All of it is just temporary information structure appearing inside the fluctuation. That is the part that makes modern cosmology begin to become almost frightening on a philosophical level. Because according to pure probability theory, such a brain is far more likely to appear than an entire universe, with a history stretching billions of years. Remember the basic logic. Smaller fluctuations always have higher probability than larger ones. And if all you need is an observer with subjective experience, then creating a single brain is always cheaper in terms of entropy than creating an entire cosmos. This is no longer astronomy. This is the point where physics begins to question the very foundation of perception. And what makes many cosmologists truly uncomfortable is that the Boltzmann brain problem cannot be easily dismissed with a few simple philosophical sentences. It arises as a direct consequence of thermodynamics, entropy, and thermal fluctuations. You cannot just say, that sounds too absurd, so it must be wrong. Physics does not work according to human comfort. In the history of science, many things that once sounded absurd turned out to be true. Quantum tunneling sounded absurd. Time dilation sounded absurd. Superposition sounded absurd. But nature has never cared what seems reasonable to our evolved intuition. That is the most frightening part. What makes physicists uneasy is not the image itself of a brain floating in vacuum, What makes them uneasy is that mathematics does not easily refute it. If a cosmology model leads to Boltzmann brains dominating in probability, that model begins to have serious problems. Because if most observers in the universe are Boltzmann brains with false memories, then we no longer have solid reason to believe that our own memories reflect a real history. Do you see what just happened? Cosmology just pulled the observer themselves into the physics problem. For most of the history of science, we studied the outside world, planets, stars, atoms, gravitational force. But here physics begins to question even the trustworthiness of the observer's experience. That is the moment when cosmology truly turns into existential physics. Science is no longer just studying the stars. It begins to study the reliability of perception. And that is why many cosmologists view the Boltzmann brain problem as an extremely serious warning sign. Today, many modern cosmology models are actually evaluated based on whether they avoid Boltzmann brain domination or not. If a model predicts that most observers must be Boltzmann brains, physicists begin to suspect that something is wrong with that model. But even that does not make the problem disappear completely. It only shows that this paradox is serious enough to force cosmology to change direction. The strange thing is that all of this started from entropy, from statistical mechanics, and from a completely reasonable effort to understand why the universe has order. That is the part I always find both beautiful and frightening about physics. You start with a few simple equations describing heat and probability, and suddenly they lead you to the question of whether your own memories reflect a real history. And if a fake brain has a higher probability than a real universe, then the most dangerous question begins to appear. Where exactly are we in the whole picture? What makes the Boltzmann brain paradox so dangerous is that it attacks an assumption that almost every human takes for granted, that memories reflect a sequence of events that actually happened. You wake up in the morning and believe that yesterday existed. You believe you have a childhood, a family, a history, a physical world that continuously existed before you opened your eyes today. All of human experience is built on that assumption. And in fact, all of science is too. We observe, remember, compare data, build models, test predictions. Everything depends on memories and observations, reflecting a relatively stable objective reality. But the Boltzmann brain paradox puts a knife straight into that foundation. Because if an observer can appear as a random fluctuation together with an entire set of false memories, then subjective experience is no longer certain evidence that the past actually existed. That is the part that makes cosmology begin to touch regions that only philosophers use to discuss. And the strange thing is that all of this did not start from philosophy. It started from statistical mechanics, from entropy, from probability. That is what makes many physicists the most uncomfortable. If this were just a classic brain in a vat thought experiment from philosophy, many physicists would dismiss it fairly quickly. But the Boltzmann brain paradox arises from serious physical logic itself. If smaller fluctuations have higher probability than larger ones, and if a single brain requires far less entropy reduction than an entire complete cosmos, then pure probability seems to favor the existence of isolated observers with false memories over a universe history stretching billions of years. That is the frightening part. Not that the idea sounds weird, but that the logic continues to work as you go deeper into it. Think about how dangerous this is for science. Science operates on the assumption that our observations are fundamentally trustworthy. We may make measurement errors. We may misunderstand data. But we always assume that there is a stable physical world underneath those observations. If that assumption collapses, the scientific method begins to lose its foundation. Because if your memories could just be a random fluctuation that appeared a few seconds ago, then all the evidence you think you have about the past becomes uncertain. The galaxies you see may never have existed. Earth may never have had billions of years of history. Even this conversation, according to the extreme logic of the paradox, could be just temporary information appearing inside an extremely rare low entropy fluctuation. And that is where cosmology begins to intersect with epistemology, the branch of philosophy that studies the nature of knowledge itself. Physics now no longer just asks, how does the universe work? But also asks, how do we know anything is real? I think this is one of the strangest moments in the history of science. The equations once created to describe heat and probability now begin to question the very reliability of the people using them. That is why many cosmologists view the Boltzmann brain problem as a very serious red flag for any cosmology model. If a theory leads to most observers in the universe being Boltzmann brains, physicists begin to suspect that the theory has something wrong at a fundamental level. Because if your theory predicts that most observers are isolated fluctuations with false memories, then that theory also destroys the reason to trust the very data used to build it. Do you see the dangerous loop here? A cosmological model cannot destroy its own ability to trust observations and still hope to be considered a stable description of reality. And this is a very important part. Physicists are not afraid of strange ideas. Modern physics is already full of strange things. We have gotten used to electrons behaving like waves, space-time curvature, quantum tunneling, and black holes evaporating through Hawking radiation. What truly makes physicists uneasy is strange ideas where the mathematics continues to be correct. In science, the most frightening thing is not imagination. It is consistency. Because if the equations keep working, you cannot simply reject the conclusion just because it offends your intuition. And the history of physics has shown many times that human intuition is often the one that fails. That is why the Boltzmann brain paradox is taken seriously, even though most physicists hope something will eventually solve it. Perhaps future quantum gravity theories will eliminate this problem. Perhaps entropy behaves differently at cosmological scales. Perhaps current eternal inflation models are not yet complete. But until then, the paradox remains there like a small but very uncomfortable crack beneath the foundation of modern cosmology. And sometimes I think that is the most frightening thing about science. Not that we do not know enough, but that mathematics sometimes leads us to places where human intuition absolutely does not want to go. That is why physicists are often very cautious when talking about these kinds of issues in front of the public. It is not because they are hiding some cosmic secret in the style of conspiracy nonsense. Most scientists hate that kind of thinking. The real reason is much simpler. Ideas like the Boltzmann brain are very easily misunderstood as nihilism, mysticism, or pseudoscience if they are detached from their mathematical foundation. A person might hear a few sentences about false memories and conclude that science is saying nothing is real. But that is not what cosmology is doing. What physics is really saying is more subtle and also much more worrying. Some current models of the universe lead to logical consequences that even the physicists themselves are not comfortable with, and most cosmologists view that as a sign that the model is not yet complete, rather than the final truth. This is extremely important to understand correctly. In science, a paradox usually does not mean reality is wrong. It usually means our understanding is missing something. But science does not work by avoiding uncomfortable conclusions. If the equations lead to a strange result, you have to follow it all the way before rejecting it. That is what makes science different from ordinary belief systems. In many belief systems, an idea will be discarded if it causes emotional or philosophical discomfort. But physics does not care what makes humans comfortable. If the data and mathematics continue to agree with each other, you must face their consequences whether you like it or not. And the history of science is full of such moments. There are many major discoveries that began as results that everyone hoped were wrong. When quantum mechanics appeared, many physicists thought it was too strange to be true. Einstein hated the idea of randomness at the fundamental level. Schrödinger hated the interpretation of the equation he himself created. Dirac once said that if you are not shocked by quantum mechanics, perhaps you have not understood it. But the problem is that experiments kept confirming it time after time. Nature does not change just because human intuition objects. And I think that is one of the most uncomfortable but most important lessons of 20th century physics. The human brain evolved to throw stones, hunt, recognize faces, and survive in everyday reality. It is not optimized to understand black holes, quantum fields, or cosmological entropy. We often forget that. We tend to think that whatever seems reasonable to our intuition must be closer to truth. But the history of physics shows that the opposite has happened many times. Relativity says that time flows differently depending on velocity and gravity. Quantum mechanics says that a particle does not have a definite position until measurement occurs. Vacuum fluctuations say that empty space is not truly empty. None of those things seem reasonable to common sense. But nature has never had an obligation to make reality comfortable for our evolved brains. That is the part that makes modern cosmology both beautiful and frightening. It continuously pushes humans to the limit of intuition. And sometimes the most mature thing science can say is not we have the answer, but we do not yet understand this. I think the public often underestimates the level of genuine humility that exists in serious physics. The best scientists I have ever met are usually the ones most comfortable with uncertainty. They do not like to pretend to know more than the data allows. That is why cosmologists do not like to speak too strongly about Boltzmann brains or pre-Big Bang cosmology on television. It is not because they are afraid of the truth. They are afraid of oversimplification. Because when these extremely subtle ideas are turned into sensational headlines, the real logic underneath them often disappears completely. But whether we like it or not, those paradoxes still exist beneath modern cosmology. They are like signals indicating that somewhere inside our models there may still be a deeper principle that has not yet been discovered. Perhaps future quantum gravity theories will solve them. Perhaps entropy behaves differently at cosmological scales. Perhaps we are misunderstanding vacuum, time, or observer selection. No one knows for sure. And in fact, that is the normal state of frontier science. What I find interesting is that modern cosmology is beginning to touch the limit where human intuition is no longer a reliable tool. When you go deep enough into reality, physics begins to look less like how the world works and more like something far more alien than anything our evolved brains were ever prepared to understand. It is at that point that modern cosmology begins to slide into another idea that is almost as controversial as Boltzmann brains. The anthropic principle. This is one of the concepts that many physicists both use and do not feel entirely comfortable with. The basic idea sounds fairly simple. We observe the universe the way it is because if the universe were too different, there would be no observers existing to observe it in the first place. It sounds almost obvious, right? But when you begin to apply that logic to cosmology, everything quickly becomes strange. Because many fundamental constants of physics seem to lie within an extremely narrow range that allows complex structure to exist. Gravity, for example, is enormously weaker than electromagnetism. If gravity were only slightly stronger, stars might burn too quickly for life to evolve. If much weaker, matter might never clump into galaxies and stars. Similarly, if the electromagnetic force changed slightly, stable atoms might not exist. Carbon chemistry might not form. Without complex chemistry, there would be no biology. And the strange thing is that the deeper we look into particle physics and cosmology, the more we see numbers that seem fine-tuned in a very uncomfortable way. The cosmological constant is the most famous example. Its value is small to the point of being almost absurd by quantum field theory standards. But if it were significantly larger, space would expand too quickly for galaxies to form. Do you see the problem starting to appear yet? Our universe seems to sit right in the narrow region that allows complexity to exist. And the anthropic principle says that perhaps that is not as surprising as we think, because only universes suitable for observers would have people asking questions about them. But this is a very important part. Anthropic reasoning does not actually explain why the constants have the values they do. It only filters out the universes where observers can exist. That is why many physicists feel uncomfortable with it. In physics, we usually want deeper explanations. We want to know why gravity has its current strength, why the electron mass is what it is, why vacuum energy is strangely small. Anthropics is sometimes seen as a way of saying everything is this way, because otherwise we would not be here. And for many physicists, that sounds more like surrender than explanation. But then multiverse models began to appear, and the anthropic principle suddenly became much more serious. If eternal inflation really creates countless bubble universes with different physical constants, then anthropic selection begins to make statistical sense. Perhaps we do not live in the only universe. Perhaps we only live in one of the rare universes where observers can exist. That is when the observer begins to enter cosmology in a very dangerous way. For most of the history of physics, the observer was seen as something standing outside the physical system. You study electrons, stars, or black holes without caring who is observing them, but quantum mechanics began to blur that boundary, and modern cosmology is pushing it even further. Because if the existence of observers affects the kind of universe being observed, then the observer is no longer a minor factor. It becomes part of the problem. This makes many physicists extremely uncomfortable because it seems to undermine the classical dream of physics, finding a completely objective explanation for reality. Some cosmologists even view the anthropic principle as a sign of failure in explanatory physics. According to them, if you have to use anthropic reasoning, it means you have not truly understood the deeper mechanism behind the physical constants. And perhaps they are right. But science has no obligation to give us the kind of explanation we like best. If the data and equations keep pointing in that direction, physicists are forced to at least consider it seriously. What is interesting is that modern cosmology is increasingly moving toward a place where physics, probability, and observer selection blend together in a way never seen before in the history of science. The observer is no longer a spectator standing outside the universe. The very existence of the observer begins to affect how we interpret reality. That is an idea extremely alien to human intuition. We like to think we simply see the universe as it is. But anthropic reasoning suggests that our existence has automatically filtered out a very special small portion of everything that could exist. And that is where cosmology begins to become truly strange. Because when the observer steps into the equation, reality no longer resembles a simple objective machine. It begins to resemble something deeper, stranger, and harder to separate from our own act of existing and observing. That is where string theory enters the story. And I have to be honest that this is one of the boldest efforts modern physics has ever attempted. For decades, physicists have tried to unify quantum mechanics with gravity into a single framework. That is the biggest unsolved problem in theoretical physics. Quantum mechanics describes the microscopic world extremely accurately. General relativity describes gravity and the structure of space-time extremely accurately. But when you try to put them together in the same set of equations at extremely high energies, for example, near the Big Bang or inside black holes, everything begins to collapse. String theory appeared as an effort to solve that problem by completely changing the way we think about fundamental particles. Instead of dimensionless point particles, the theory says that the foundation of reality may be tiny strings vibrating in many different modes. Those vibrations create different particles, just as violin strings create different notes. This idea is extremely beautiful mathematically. And what is remarkable is that gravity automatically emerges inside that framework instead of having to be added from the outside. That is why string theory excited many physicists for a very long time. But then another problem began to appear. It turns out string theory does not predict a single universe. It allows an enormous number of different vacuum states. Vacuum here does not mean simple empty space. It is the background state of all the fields and geometry in the theory. And the strange thing is that different vacuum states can lead to different laws of physics, different electron masses, different forces, different numbers of dimensions, different chemistry. Even the entire structure of reality can be different. This leads to what is called the string landscape problem. Instead of a single solution for the universe, the theory seems to allow a gigantic landscape of nearly countless possible universes. Some estimates even give numbers like 10 to the power of 500 possible vacuum states. Now pause for a moment and think about that. For most of the history of physics, we hoped there would be a single set of equations explaining why the universe has to be as it is now. But the string landscape suggests the opposite. Perhaps reality did not choose a single universe. Perhaps every mathematically consistent configuration exists somewhere. And that is when the multiverse moved from speculative philosophy into serious theoretical physics. I know the word multiverse sounds very Hollywood, but what is important is that many physicists did not come to it because they like science fiction. They were pushed there by mathematics. Eternal inflation combined with the string landscape began to create a picture where countless bubble universes can appear with slightly different laws of physics. Some universes will collapse almost immediately. Some will never create stable chemistry. Some may never form stars. And in an extremely rare few, complexity, biology, and observers can appear. At that point, the anthropic principle suddenly becomes less uncomfortable statistically. If there are countless universes, then the fact that we exist in a universe suitable for life is no longer too strange. Of course, observers will always find themselves in places where observers can exist. This solves some mysteries, especially the fine-tuning problems. But at the same time, it opens up much larger questions. Because if reality contains nearly countless universes, then what really makes our universe special? And does special even have meaning anymore? That is the part that makes many physicists uncomfortable. Science traditionally seeks deeper and simpler explanations. But the landscape picture seems to go in the opposite direction. Reality does not become simpler as you go deeper into the foundation. It becomes larger and more chaotic. But the history of science sometimes works exactly like that. We solve one mystery and then discover an even larger mystery underneath it. Newton explained planetary motion and then opened the question of what gravity really is. Quantum mechanics explained atoms and then destroyed classical intuition. Relativity explained gravity and then turned space-time into something that can curve and expand. Physics often progresses by replacing certainty with a deeper layer of uncertainty. And the multiverse may be the largest example of that. What is important is that the multiverse is not simply fantasy added to make reality sound cooler. It appears as a natural consequence of many serious mathematical frameworks. The biggest problem right now is not a lack of ideas. Theoretical physics is full of ideas. The problem is a lack of direct experimental access. We cannot step into another bubble universe to test it. We cannot build a particle accelerator the size of a galaxy to probe Planck-scale physics. That is where modern cosmology encounters a very uncomfortable limit between mathematics and observation. Some physicists see that as a sign of danger. Others see it as the natural frontier of science. But no matter which side you stand on, one thing is becoming increasingly clear. The deeper you look into the foundation of reality, the less the universe resembles a simple design built for human intuition. It begins to resemble a vast, multi-layered structure far more alien than anything classical physics ever imagined. What is even stranger is that the more we try to understand the deepest foundation of reality, the more physicists begin to suspect that even time itself may not be fundamental. This is extremely difficult to accept for human intuition because we live completely inside the flow of time. We feel it passing. We remember the past, experience the present, and imagine the future. In everyday life, time seems so absolute and continuous that it is almost impossible to doubt. But physics has shown many times that the most obvious things are often illusions at a deeper level. Einstein destroyed the idea of absolute time at the beginning of the 20th century. In relativity, time does not flow the same for every observer. Gravity slows time down. Velocity stretches time out. Two people experiencing different conditions can measure time differently without either being wrong. That alone is strange enough. But quantum gravity may be pushing the issue much further. Some modern models are beginning to suggest that time is not the foundation of reality, but only an emergent phenomenon, like temperature emerging from the motion of billions of molecules. In other words, time may not exist at the deepest layer of physics. It may only appear when the universe reaches a certain level of structure. One of the places where this idea appears most clearly is the Wheeler-DeWitt equation, a famous equation in canonical quantum gravity. What shocked physicists when they first looked at it is that time almost disappears from the equation. Hat h spy 0. In ordinary quantum mechanics, you almost always see evolution in time. But in the Wheeler-DeWitt equation, the universe at the overall level seems not to evolve in time, in the way we are used to thinking. This leads to what is called the problem of time in quantum gravity. If the fundamental equations do not contain time as a basic variable, then where does our sense of time come from? That is one of the deepest questions in modern physics, and this is where many cosmology paradoxes may originate. We keep asking what happened before the Big Bang, but perhaps that question is built on a wrong assumption from the very beginning, because the word before already implicitly assumes the existence of time. If time itself only appears after some physical process, then asking what happened before time may be like asking what is north of the North Pole. Our language begins to hit its own limits. This sounds extremely uncomfortable to everyday intuition, but remember that human intuition evolved in everyday physics environments, not quantum cosmology. Our brains are optimized to catch apples, run from predators, and recognize patterns in meter and second scale environments. They were not built to understand Planck scale reality or pre-Big Bang physics. We often forget that and unconsciously apply everyday common sense to the extreme conditions of the universe. And that is when paradoxes appear. Many paradoxes in cosmology may not be because reality is contradictory, but because we are using concepts evolved for everyday life to try to describe something that lies far beyond our biological intuition. Modern physics continuously forces humans to accept things that common sense hates. There is no absolute simultaneity. Empty space is not truly empty. Particles do not have a definite state before measurement in the classical way. And now perhaps even time is not fundamental. This does not make science weaker. On the contrary, I think it shows that nature is far more profound than anything common sense ever imagined. One of the biggest mistakes humans often make is believing that reality must work the way our brains want it to. But the history of physics is the history of intuition being continuously defeated by mathematics and observation. We once thought Earth stood still. We once thought time was universal. We once thought causality was simple and linear. Each time science goes deeper, reality becomes a little more alien. And perhaps the most frightening thing is not how strange the universe is. Perhaps the most frightening thing is that we still insist on describing it using a language and intuition created for a completely different world. Because if time is truly emergent, if it is only a phenomenon that appears at a certain scale of reality, then our entire way of thinking about beginnings and endings may need to be rewritten from scratch. And in that case, before the Big Bang may not be an undiscovered moment. It may simply be the place where human language begins to lose its ability to describe reality in a meaningful way. That is where cosmology begins to touch on a question that, for most of the history of science, physicists have almost tried to avoid: consciousness and the role of the observer. Every time physics mentions observer, a ton of mystical nonsense immediately appears. But the observer problem in quantum mechanics is real, and it has made physicists uncomfortable for nearly a century. In classical science, we once assumed that the observer could stand outside reality like a neutral spectator. The universe exists in its own way, and the scientist simply measures what is already there. But quantum theory began to make that assumption very difficult to maintain. In the double-slit experiment, for example, the behavior of a particle depends on whether measurement occurs or not. I am not saying consciousness creates reality in the style of New Age fantasy. That is not physics. But it is clear that quantum mechanics forces us to rethink the relationship between the observer and the observed system. And when you move from quantum mechanics to cosmology, that problem becomes much stranger. Because in cosmology, the observer does not stand outside the system being studied. We do not observe the universe from outside the universe. We are inside the very system itself. This is what makes cosmology an extremely unusual science. In almost every other field of physics, you can separate the observer from the object of study, at least in theory. But with the entire cosmos, that is impossible. There is no outside perspective for the universe. There is no place outside space-time to stand and view all of reality as a complete object. And this creates very strange logical problems, because when the observer is part of the system, their observations then can be affected by selection effects in extremely profound ways. Anthropics is one example. We observe a universe suitable for life, because only in that kind of universe do observers exist. But observer selection can affect the way we interpret cosmological data even more deeply. Think about Boltzmann brains again. The entire paradox arises because the observer is no longer something on the side. The existence of the observer begins to become a variable inside the equations. That is what makes many physicists feel uncomfortable, because traditional science has always tried to aim for absolute objectivity. We like to think reality exists completely independently of whether anyone is observing it or not. And at everyday scales, that assumption works extremely well. But at quantum scales and cosmological scales, the boundary begins to blur in a very uncomfortable way. This does not mean consciousness creates the universe. I want to make that very clear. Modern physics has not proven anything like that. But it is pointing out that the observer may not simply be a passive camera recording reality from the outside. And the deeper we research, the closer cosmology gets to questions that once belonged to deep philosophy. What counts as an observer? What is information at the fundamental level? What does measurement really mean? Why does the universe have structure that allows conscious systems to appear? These were once territory that many physicists did not want to touch for fear of sounding too philosophical. But the problem is that reality does not seem to care about the academic boundaries. Humans create. If the equations lead to philosophical questions, science is forced to face them. And I think this is one of the most interesting things happening in modern cosmology. The more we study the universe, the more we are forced to study the very limits of human cognition. Not just what is out there, but also to what extent can our brains understand reality? Because the observer itself is a product of the universe. Consciousness does not appear from outside physics. It appears inside physics. And that creates a very strange loop. The universe is trying to understand itself through tiny self-aware structures born inside it. I have always found that both beautiful and frightening. A brain made of atoms, existing on a small planet around an ordinary star, can ask questions about the origin of space-time itself. But at the same time, that very brain is limited by its evolutionary history, sensory limitations, and intuition designed for survival, rather than truth at cosmological scales. Perhaps that is why reality becomes increasingly difficult to understand as physics goes deeper. Not because the universe is irrational, but because we are hitting the natural limits of evolved cognition. And perhaps the strangest thing that modern cosmology is gradually revealing is that the observer has never truly been separate from reality the way classical science once imagined. That is probably the most uncomfortable lesson that modern physics is trying to teach us. The universe may not care at all about what seems reasonable to the human brain. I think many people unconsciously assume that if we are smart enough, reality will eventually become intuitive and easy to understand. But evolution has never optimized our brains to understand quantum gravity or cosmology. Evolution only optimized us well enough to survive on a small rocky planet at everyday life scales. The human brain is good at recognizing faces, predicting the motion of medium-sized objects, understanding simple causes, and avoiding danger. That is the environment our intuition was built for. No one evolved to intuit curved space-time or vacuum fluctuations. And that is why quantum mechanics and relativity always feel off to human instinct. Our common sense is programmed for low speeds, weak gravity, and everyday scale objects. But reality at deeper levels has no obligation to resemble the environment evolution prepared us for. In quantum mechanics, particles can behave like waves. An electron can interfere with itself. Quantum tunneling allows particles to cross barriers that classical physics says are impossible to cross. Vacuum is not truly empty, but continuously fluctuates with virtual particles appearing and disappearing. Relativity says that time slows down near strong gravity or at high velocity. There is no absolute simultaneity. Space-time can curve, vibrate, and even expand on its own. Every major discovery of modern physics carries the same message. Reality was not built to fit human evolved intuition. And the interesting thing is that the first human reaction is almost always the same. We say, that sounds absurd. But the history of science shows that sounds absurd is an extremely poor standard for judging truth. There was a time when people thought the Earth moving around the sun was absurd. There was a time when atoms were considered fantasy. There was a time when non-local quantum effects were seen as impossible. Einstein once called quantum entanglement spooky action at a distance because even he was not comfortable with it. But nature does not change to protect our common sense. And that is why physics is forced to become ruthless in a certain sense. An idea sounding strange is not evidence against it. The only thing nature cares about is mathematics and experimental consistency. If the equations correctly predict reality time after time, physicists are forced to take them seriously, no matter how much they offend intuition. I think many people underestimate how radical this is. Science does not just give us new facts. It continuously destroys the way the human brain wants to think about reality. And modern cosmology is pushing that process to its final limit. We are trying to understand the origin of space-time with a brain evolved to avoid predators in the savannah. We are using language created for everyday objects to describe the quantum vacuum and Planck scale physics. It is no surprise that reality starts to sound like science fiction. Perhaps the truly strange thing is not that the universe is so difficult to understand. Perhaps the truly strange thing is that mathematics even allows us to understand any part of it in the first place. Eugene Wigner once called that the unreasonable effectiveness of mathematics. Abstract symbols created by the human brain describe reality with almost unimaginable accuracy. And when mathematics conflicts with intuition, physics repeatedly shows that mathematics usually wins. That does not mean science becomes weaker when reality becomes less intuitive. On the contrary, I think it shows that nature is far more profound than any simple model that common sense has ever built. Some people react to this by rejecting modern physics entirely because it does not make sense. But that is a big misunderstanding of science. The goal of physics is not to protect the comfort of human intuition. The goal of physics is to describe reality as accurately as possible. If reality is weird, science must accept that reality is weird. That is intellectual honesty at its highest level. And perhaps this is what makes modern cosmology both beautiful and frightening. It is bringing humanity to the final edge of intuition. We are beginning to touch layers of reality where concepts like time, space, causality, and observer no longer work the way the everyday mind expects. Each new step forward makes the universe less like a simple machine and more like something deeper, more alien, almost not designed for human cognition. Perhaps the most frightening thing is not how strange reality is. Perhaps the most frightening thing is the possibility that the universe was never designed to be understandable to us in the first place. The interesting thing is that many people look at all of this and feel that science is making the universe colder, less meaningful, or less mysterious. I have never understood that feeling. For me, the opposite is true. The more you understand physics, the more reality becomes miraculous in a way that is hard to put into words. When you are a child, you can look at the night sky and see a few beautiful bright dots. But when you understand that each bright dot could be a star millions of times larger than the sun, that its light has traveled thousands or millions of years to reach your eyes, that the atoms in your body were forged inside the cores of stars that died long before Earth existed, then the universe does not shrink. It becomes deeper. I think many people confuse mystery with ignorance. They fear that if science explains something, its beauty will disappear. But physics has never made reality less miraculous. It only replaces simple stories with layers of structure that are far more astonishing. The real beauty of science lies in the fact that nature is always more complex than our initial imaginations. Every time we think we are close to the final answer, the universe opens up a new layer of questions underneath it. We once thought atoms were tiny, hard, solid balls. Then quantum mechanics appeared and turned them into probability clouds. We once thought space and time were the fixed stage of reality. Then relativity turned space-time into something that can curve, expand, and vibrate. We once thought vacuum was absolute nothingness. Then quantum field theory showed that empty space is full of invisible fluctuations. And now modern cosmology is making us question even the origin of time, the role of observers, and the deepest structure of reality itself. That does not make the universe less meaningful. It makes the universe larger than our imagination. I think uncertainty makes many people uncomfortable because humans like the feeling of certainty. We want reality to be neat, stable, and easy to understand. But science does not exist to provide emotional comfort. It exists to discover what is actually true, even when the truth makes our intuition collapse. And paradoxically, that is exactly what makes science beautiful. Curiosity is stronger than the need to feel philosophically safe. A good scientist does not love certainty. They love discovery. They accept that every real answer usually only opens up larger questions. I think that is one of the most beautiful qualities of the human mind. We are tiny creatures on an ordinary planet, yet we have the ability to look up at the universe and ask how it was created. And the strange part is that the universe seems to allow us to understand at least part of the answer through mathematics and observation. That is almost the most miraculous thing I can imagine. Not knowing the answer is not a failure of science. It is the very engine of science. Every major advance in physics began with someone honest enough to say, "There is something here that we do not yet understand." Newton did not explain what gravity is. Einstein did not explain why space-time exists. Quantum mechanics did not explain why measurement creates definite outcomes. Science always advances by accepting ignorance before overcoming it. And modern cosmology is placing humanity before the biggest questions that have ever existed. Is time fundamental? Is the universe unique? Does reality exist independently of observers in the way we think? Is there anything before the Big Bang, or is the question itself meaningless? These are no longer small questions about the mechanics of stars or galaxies. They are questions about the foundation of existence itself. And what excites me is not that we have the final answer. It is that we continue to ask questions, even knowing that reality may forever exceed our intuition. Perhaps that is the most mature thing science teaches humans, to accept uncertainty without abandoning reason. Because in the end, the most wonderful thing about the universe may be that it is always larger than the models we create to understand it. What really worries many physicists is not the fact that we do not know enough. Science always exists in a somewhat incomplete state. What is much more worrying is when mathematics continues to work, even as our intuition begins to collapse completely. In the history of physics, the most dangerous moments usually appear exactly at that point, when data and common sense begin to contradict each other strongly. At the beginning of the 20th century, classical physics seemed nearly complete. Then blackbody radiation, the photoelectric effect, and atomic spectra began to appear as small cracks in the old theory. At first, they looked like technical anomalies, but ultimately they led to quantum mechanics and destroyed nearly all classical intuition about reality. Relativity was the same. Newtonian mechanics worked extremely well at everyday scales, but then data began to show that time and space do not behave as humans once believed. Every major revolution in physics began with a very uncomfortable moment when equations and intuition no longer went together. And modern cosmology is entering exactly that kind of phase. We have models that work very well at many levels. General relativity predicts gravitational lensing, black holes, and cosmic expansion extremely accurately. Quantum field theory predicts particle interactions with almost absurd precision. Inflation explains large-scale structure remarkably well. But when these frameworks are pushed to the final limits of reality, they begin to lead to extremely counterintuitive conclusions. The Boltzmann brain problem is a perfect example. This is not a small philosophical joke that the internet likes to turn into a meme. It is a sign that some cosmological models may be missing an extremely important component. Because if your equations lead to a universe where fake observers are more probable than observers with genuine cosmic history, then something has gone deeply wrong somewhere. And that is the part that makes physicists truly uneasy. Scientists are not afraid of mystery. Mystery is the fuel of science. What they fear is the possibility that a theory could destroy the very foundation that allows science to function. The entire scientific method is based on the assumption that observers can obtain relatively reliable information about reality. We may make errors, we may have biases, but ultimately there exists a stable external reality sufficient for observations to be meaningful. If that assumption is no longer solid, cosmology will have problems at the foundational level. Because if most observers in the universe are only random fluctuations with false memories, then our belief in observational evidence itself begins to become hard to defend. That is why Boltzmann brain domination is viewed as a serious red flag. Many cosmologists today actively try to build models that avoid that conclusion precisely because it threatens the epistemic stability of science. A cosmological theory cannot simultaneously explain the universe and destroy the ability to trust the observations used to build it. If that happens, the theory is cutting off its own logical foundation. And what is fascinating is that physics is no longer just studying matter, energy, and space-time. It is beginning to study the conditions necessary for knowledge itself to exist. That is a very strange shift in the history of science. We began by measuring the motion of planets. Then we discovered atoms, fields, and quantum mechanics. And now cosmology is asking an even deeper question. Under what conditions can observers reliably know anything about reality at all? That sounds closer to philosophy than traditional physics, but reality does not seem to care how humans want to divide disciplines. If the equations lead to those questions, science must follow them. I think this is the part that is both beautiful and frightening about modern cosmology. We are living in a time when physics is not only trying to understand the universe, but also trying to understand the limits of understanding itself. And perhaps the most unsettling thing is this. Every time science goes deeper, reality becomes less like a simple machine and more like something capable of collapsing the very intuition that helps humans feel safe inside existence. Physics once made us realize Earth is not at the center of the cosmos. Then it showed that time is not absolute. After that, quantum mechanics destroyed intuition about causality and locality. Now, modern cosmology is beginning to touch something even deeper, the reliability of the observer itself. And I think that is when science becomes truly frightening. Not when it says how large the universe is, but when it begins to question the very foundation of the perception we use to understand the universe in the first place. That is where a very uncomfortable possibility begins to appear. Perhaps the question, what happened before the Big Bang, is not even a properly formed physics question from the start. I know that sounds like a language game, but it is actually much deeper than that. We often forget that human language was created for everyday life experiences, rather than to describe quantum cosmology. Words like before, after, inside, outside, cause, or beginning were all formed from the experiences of living creatures in a meter and second scale environment on the surface of Earth. But when physics moves toward the extreme conditions near the origin of space-time, those concepts begin to lose the stability we are familiar with. Take the word before, for example. It always implicitly assumes that time exists as a continuous linear flow. But if time itself only appears after the Big Bang, then asking what happened before time may be a category error. It is like asking, where is north of the North Pole? The question sounds grammatically correct, but its logical structure may have been wrong from the very beginning. And that is the reason many paradoxes in cosmology appear. We keep trying to apply the intuition of everyday reality to layers of reality where that intuition may no longer function. In everyday life, everything has a cause that occurs before the result. Objects exist in space. Time flows continuously, but relativity already began destroying those assumptions long ago. Einstein showed that simultaneity is not absolute. Two different observers may not agree on what happened before or after if space-time geometry is different. Time is no longer a universal clock running the same for the entire cosmos. And quantum gravity may go even further. Some modern approaches suggest that space-time itself is only an emergent structure appearing from a deeper layer of reality, where concepts like distance and duration do not even exist in the familiar sense. This is extremely difficult to imagine because all of human cognition depends on space-time intuition. We cannot imagine experience without a somewhere and a sometime. But physics repeatedly shows that reality has no obligation to fit the cognitive architecture of human beings. If space-time is emergent, then the Big Bang may not be the absolute beginning of existence, as everyday intuition thinks. It may only be a phase transition, a physical transition point, where space-time as we know it begins to appear from a deeper structure. Just like the way temperature emerges from the collective motion of atoms, even though an individual atom does not have temperature in the ordinary sense. Some quantum gravity models are indeed moving in that direction. In loop quantum cosmology, for example, the Big Bang may be replaced by a quantum bounce. In some holographic approaches, space-time may emerge from a deeper entanglement structure. And in the Wheeler-DeWitt framework, time almost disappears from the fundamental equation altogether. That is the reason many modern physicists are extremely careful with language when talking about the origin of the universe. They avoid using overly confident phrases like the absolute beginning, because current mathematics does not yet allow that kind of confidence. What is interesting is that the deeper we go into cosmology, the more science becomes humble rather than arrogant. Those who understand frontier physics best are usually the ones most comfortable with uncertainty. They know that concepts the everyday mind views as obvious may only be emergent approximations of a much deeper layer of reality. And I think this is the part that is both beautiful and unsettling about modern cosmology. We start with a very simple question. What happened before the universe? But the deeper we go, the more physics forces us to question the very structure of that question. Perhaps we are trying to use language evolved for hunting, survival, and social interaction to describe a layer of reality where time, causality, and space-time themselves do not exist in the familiar sense. And that is when science becomes truly strange. Not when it gives us answers that are too strange, but when it makes us realize that perhaps some of humanity's most intuitive questions were built wrong from the very beginning. Because sometimes the most dangerous thing is not that we do not yet know the right answer. Perhaps what is much more dangerous is the possibility that we may not even know how to ask the right questions about reality. What is truly strange is that many people once believed that science would eventually make the universe simpler, less mysterious, and completely explainable in a way comfortable for human intuition. But modern cosmology is doing almost the opposite. The deeper we go into the foundation of reality, the more we see the universe becoming stranger than most mythologies humans have ever created. Think about what modern physics is seriously considering right now. A multiverse with countless universes having different laws of physics. Cyclic cosmologies where the Big Bang is not an absolute beginning, but only one phase in a sequence of cosmic cycles stretching nearly endlessly. Emergent space-time where time and space themselves are not fundamental, but only appear from a deeper layer of reality. Vacuum fluctuations where empty space is full of invisible quantum activity. Boltzmann brains, where observers can appear with false memories inside thermal fluctuations. If you told these ideas to a 19th century physicist, he would probably think you were writing metaphysical fiction rather than physics. But the biggest difference is that science does not build these ideas from belief or revelation. It is pushed there by data and mathematics. That is the part that makes modern cosmology both beautiful and unsettling. The strangest conclusions of physics usually do not appear because scientists want reality to sound more dramatic. They appear because the equations continue working, even when intuition collapses. And the history of science repeatedly shows that nature was not designed around human common sense. Quantum mechanics does not care how absurd superposition sounds. Relativity does not care how much time dilation offends intuition. Vacuum fluctuations do not care that humans want nothingness to be truly empty. Modern physics continuously shows that reality is far deeper than the categories the everyday mind creates. Even the concept of nothing begins to collapse when you look deep enough. In everyday philosophy, nothingness means absolutely nothing exists. But the quantum vacuum is not nothing in that sense. It is the lowest energy state of quantum fields, still full of fluctuations and potential structure. This is extremely important. When physicists say the universe may emerge from the quantum vacuum, they are not saying something came from absolute nothingness in the popular philosophical sense. They are saying that what we once called empty turns out to have much deeper physical structure. And that is the reason vacuum fluctuations become frightening in a certain sense. They suggest that absolute emptiness may not exist in reality. Perhaps nothingness itself is an unstable concept at quantum scales. I think this is where modern cosmology begins to blur the boundaries between physics, mathematics, and deep philosophical questions. Not because science is becoming more mystical, but because reality at frontier scales naturally leads us to fundamental questions about existence, causality, information, and observation. Some people see that and think science is failing. I think the opposite. This is a sign that we are getting very close to the current limits of understanding. When Newtonian mechanics worked, the universe looked simple and machine-like. But the deeper we dig, the more physics discovers layers of reality where common sense begins to break down. And that is exactly how science progresses. It does not advance by protecting emotional comfort. It advances by following logic wherever it leads, even when the conclusions make humans philosophically unstable. Many ideas once considered impossible have now become serious research programs. Black holes were once seen as mathematical curiosities. Gravitational waves were once doubted to exist. Quantum entanglement was once viewed by Einstein as nearly absurd. Today they are established parts of physics. That does not mean every speculative cosmological idea today will be correct. Many current models may be discarded in the future. But the history of science teaches us to be very careful when dismissing an idea just because it sounds too strange. Nature repeatedly turns out stranger than human intuition expects. And perhaps the most astonishing thing is not how strange the universe is. The most astonishing thing is that a species evolved on a tiny planet can understand any part of it through mathematics. Abstract structures created by human minds somehow map onto the architecture of reality with almost impossible accuracy. That is the part that always makes me find science beautiful instead of cold. We are not just learning facts about the cosmos. We are witnessing human cognition, touching something vastly larger than itself. And the deeper we explore, the less the universe resembles a simple machine with a few comfortable rules, and the more it resembles a vast, multi-layered structure almost beyond every initial imagination humanity has ever had about reality. The most honest thing science can tell you is this: science is not a machine for producing certainty. It is a continuous process of correcting human misunderstandings about reality. I think many people grew up with the feeling that science exists to give us final answers, complete and unchanging truths. But the history of physics shows almost the opposite. Every generation of scientists begins by believing they are getting close to the final foundation of the universe, only for nature to open up an even stranger layer of reality underneath. Newton once made the cosmos look like a perfect machine operating according to deterministic laws. Then relativity appeared and turned space and time into something flexible that can curve and change depending on the observer. After that, quantum mechanics destroyed the idea that reality at the deepest level works like classical objects with definite properties. And now modern cosmology is questioning even the origin of space-time, the nature of observers, and the structure of existence itself. That is the reason one of the most important qualities of science is not certainty, but the ability to honestly say, "We do not know." That sounds simple, but it is actually extremely difficult for human psychology. Humans like the feeling of closure. We want the universe to have a clear beginning, clear structure, and clear answers. But physics repeatedly shows that reality has no obligation to provide emotional comfort for us. The Big Bang was once seen as almost the final answer for the origin of the universe. But the deeper we research, the more the Big Bang itself becomes the starting point for even deeper questions. What caused inflation? Why was entropy initially so low? Is space-time fundamental? Did something exist before the Big Bang, or is before itself meaningless? Modern cosmology does not bring comfort. It brings humility. It reminds us that the universe may be much larger than every conceptual framework human minds have ever built. And paradoxically, it is uncertainty itself that is the engine of science rather than its weakness. If we already had final answers, physics would be over. Curiosity exists precisely because reality remains incomplete for human understanding. I think that is one of the most beautiful things about science. It does not require you to pretend certainty where certainty does not yet exist. It allows humans to live with doubt without abandoning reason. Curiosity is more important than the need to feel philosophically safe. A good scientist is not someone who always has answers. It is someone willing to follow evidence, even when it leads somewhere uncomfortable. And perhaps that is where modern cosmology stands right now. Perhaps there really was something before us. Perhaps the universe went through endless cycles. Perhaps the multiverse exists. Or perhaps the very concept of before is a sign of linguistic limits rather than physical reality. We do not know. And science works best precisely when it is honest about what it does not yet understand. I have always thought that the most beautiful part of physics is not how simple reality is. It lies in how much deeper reality is than anything common sense ever imagined. A species evolved on a small planet can explore black holes, quantum fields, cosmic expansion, and the structure of space-time using mathematics. That is almost miraculous to me. But at the same time, the more honestly we look at the universe, the more we realize our understanding is still extremely small. Each generation of physicists is only seeing a very thin slice of reality. We are like people standing before an ocean in the dark with a small flashlight, continuously discovering new details, but never seeing the entire structure at once. And the most remarkable thing is that humanity continues to ask questions, even knowing it may never have a complete final picture. That is the part that makes science profoundly human to me. We do not explore the universe because of guaranteed answers. We explore it because curiosity is stronger than fear of uncertainty. Science does not destroy mystery. It turns mystery into something that can be approached bit by bit through observation, mathematics, and intellectual honesty. Every major discovery does not make reality smaller. It makes reality stranger, deeper, and more interconnected. Quantum mechanics did not kill wonder. It created a universe even more astonishing than any ancient mythology ever imagined. Relativity did not make the cosmos colder. It turned space-time itself into something dynamic and flexible. Modern cosmology does not remove mystery from existence. It shows that mystery can run deep into the very foundation of time, causality, and observation. And perhaps the most mature thing a scientist can do is to accept uncertainty without abandoning reason, not to retreat into dogma just because reality becomes uncomfortable, not to pretend certainty where evidence is not yet sufficient, just to keep looking deeper, measuring more accurately, and asking more honest questions. I think that is the true spirit of science. Not the arrogance that we have understood everything, but the willingness to keep learning, even when the universe repeatedly destroys our intuition. And perhaps that is also the most amazing thing about reality. The more honestly we study it, the stranger, more frightening, and more beautiful the universe becomes than anything humans have ever imagined. If you want to continue exploring the deepest mysteries of the universe with me, please subscribe to the channel and turn on notifications, because there are still many questions ahead that modern science still cannot fully answer.